extended screen and put stuff on the side? No.
Well, let's do it now.
Hi, and welcome to another Building Codes training. My name is Joe Starr. I'm with Southface. Today we're going to be talking about the commercial mechanical codes, and specifically we're going to be talking about ASHRAE's 90.1 Simplified Approach compliance pathway. First, a little bit about Southface. Southface has promoted sustainable development and green building through education, research, advocacy, and technical assistance since 1978. In preparation for the launch of the new building codes in 2020, Southface and the Georgia Department of Community Affairs Building Codes Department were awarded a grant through the Georgia Environmental Finance Authority to provide many training workshops to the updates and changes on the new energy code and amendments for the state of Georgia. This video, delivered in conjunction with the Southeast Energy Efficiency Alliance, is part of a series of resources intended to further support building code compliance over the long term by giving robust insight into code changes taking effect, specifically focusing on areas of confusion that we noticed over the past year of trainings. First, I'd like to introduce the presenters today. Again, my name is Joey Starr. I'm a project manager here at Southface. We also have Hugh Magande. Would you like to introduce yourself, Hugh?
Yes. Like Joey said, Hugh Magande is the name. I'm a project technical lead here at Southface, and my background is in product development.
All right. And Burke Reeve is also here. Burke, would you like to introduce yourself?
Absolutely, thank you. Again, Burke Reeve. I'm a project manager with a company called 3 Points Planning, and a former Southfacer over a decade here with the organization. I've worked a lot on energy codes throughout the Southeast. Thanks for having me.
All right, and before we get started, I would like to point out some energy code resources that Southface has developed. Like I said, we had quite a bit of research and development and training that went into this code launch in 2020. So as such, we've presented quite a few resources here, especially the Southface website. You can go there and get your hands on this Georgia Commercial Field Guide, which is just an excellent resource that you can use in the field. And I would also encourage you to use the Georgia Energy Code Hotline, which we have an email address and phone number listed here, and you can contact us with any questions that you have regarding the code, or if you'd like any further training, you can send those inquiries there as well. So without further ado, I'd like to get into the presentation here. As I mentioned earlier, we are going to be talking about the 90.1 2013 version. We're going to be looking at the simplified approach as it relates to the HVAC compliance. And really, again, something that we've seen a lot in the field. We've had a lot of questions about this. We know that a lot of the buildings that we deal with on a day-to-day basis can qualify using this approach. So why do you think it's important, and why do you think we should use it, Bert?
Thanks, Joey. That's a great question. I think when you look at the compliance pathways within the commercial code can very quickly become quite complicated. For starters, you've got two of them. You've got the ASHRAE standard, which we are looking at here, the 90.1 2013 standard in this edition, and you've got the IECC code. And both of those could be used to permit and construct a code-compliant building in the state of Georgia. So you have to make some decisions with your commercial building about how you're going to go about achieving compliance. You have to first pick your pathway, either the IECC or the ASHRAE standard. Then once you get into the code, either the IECC or ASHRAE, you're going to see compliance pathways for your building. There are these things called mandatory provisions. These are essentially a list of rules that your building has to comply with regardless of compliance pathway. Then you have prescriptive options, a list of follow all the rules for the building, and if you check all the boxes and follow all the rules, you are deemed to comply. You have a sometimes called simple trade-off option. This is using typically the DOE's ComCheck tool, though there may be other softwares available, but most commonly people are using ComCheck reports to show that while they've traded some options, they've done a little bit more insulation over here and a little bit less someplace else in the building. Overall, their building complies with the code. The trade-off option is very useful for things like envelope and lighting, but it's relatively limited in its applicability to the mechanical section of the code. There is something called the energy cost budget method. This is a energy model, as we often refer to it in our industry. And someone could go in, use a piece of software, follow a set of standards and rules, and essentially design anything they wanted, as long as when they modeled through approved software that building they had designed, the overall building will perform as well or better than a building that met the prescriptive code. So that probably gives designers maximum flexibility and would certainly apply to the mechanical section of the code, in that you would be able to perhaps trade some things around related to your mechanical system. Of course, you're always going to have to meet the mandatory provisions. And then we have the simplified pathway. The simplified mechanical pathway is only located within the ASHRAE standard. So this is not an option if you're using the IECC, and that's important to note. So if you have a building that could use the simplified approach, you're going to need to permit it under ASHRAE. If you permit it under IECC, say for your envelope and your lighting, you're not going to be able to then use the simplified pathway, which is housed in the ASHRAE 90.1 standard, for your mechanical compliance, because you're attempting essentially to go back and forth between two different versions of a code, or two different pathways within the code. So that's important to know, that if you want to go this simplified route, your building needs to meet sort of a list of requirements and qualify as a, we'll just say, simple building. You're also going to have to be permitted under the ASHRAE 90.1 standard. And in Georgia, starting in 2020, that'll be the ASHRAE 90.1 2013 standard. So this is something that a building would really want to do, because it takes a lot of complicated information that's in the mechanical section of the code, and it distills it down to a list of, let's just kind of wave our hands and say 20 or so items that the building is going to have to do in order to show compliance. This is valuable because the majority of new commercial buildings permitted in this country actually meet the simplified building profile. The statistics that I've seen tend to say somewhere between 80 and 85% of all of the commercial building permits pulled are pulled on buildings that would meet the simple building profile. And here is that simple building profile, which essentially says if you have a building that is less than 2 stories in height, or 2 stories or less, and 25,000 square feet or less, then your HVAC systems can be deemed to comply with the requirements of the Energy Code if they can check off 18 items from a list. And those items are essentially things like, equipment functionality, zone controls, thermostat controls, and basic levels of efficiency. So what this does is takes something that could be extremely complicated, the commercial section of the Energy Code, and tries to make a simplified version of it that actually complies to a large number of the buildings that are being constructed in the real world. And hopefully in doing that, it's something that makes the code easier to both design around and easier to construct and inspect for in the real world. And in doing so, we hope that that increases overall compliance with the code by making the code requirements understandable and straightforward, and by making them easy to inspect for. And so the vast majority of commercial buildings pulled are likely to fit this small building profile of 2 stories or less and 25,000 square feet or less, and be able to use this compliance pathway for mechanical systems, which is located in ASHRAE 90.1.
Thank you very much for that, Bert. I think one thing that you brought up during that that's really important that we hear about a lot is picking one pathway versus the other, all the way up to whether you're looking at IECC or ASHRAE. Because say if you're looking at the lighting or the envelope, you might see that IECC is a little bit easier to comply with on those pathways. But if you're thinking about your HVAC, you might consider ASHRAE instead. So you definitely need to pick one or the other, and you need to do it pretty early on in the design process, so you don't start down a path that you really can't comply with in the end. So thanks for that, Bert. So I think we'll go ahead and get started looking at some of these requirements. And the first one that we're going to look at is this idea of zones. So if you want to talk a little bit about that, Bert.
Yeah, this is our first requirement. The HVAC systems must serve a single zone. This is relatively straightforward. Multi-zonal equipment becomes complicated in terms of how it is controlled and how it's delivering airflow to the different spaces within the building. If you look at the little graphic that we have on the screen, you can imagine that the one large room there might have a very different cooling demand than the small office that's located adjacent to it. So having 3 or 4 different zones of your building all connected to one piece of centralized equipment is going to basically require you to have more complicated controls and more complicated ducting to try and provide adequate comfort in each one of those zones. So because this is a simplified approach, the first thing they're saying is you can't do multi-zonal equipment because that is inherently complicated.
Yeah, right.
So you have to have single zone equipment.
So in the case of this building here, you would just basically have to have two different systems, one for the larger zone and then one for the other. So the next requirement for the simplified approach is variable airflow equipment. So basically what we're saying here is that variable fan speed really must meet certain control requirements. So Burke, if you want to kind of walk us through these control requirements, they're pretty straightforward, but it wouldn't hurt to go through them again.
Sure. The idea of variable speed equipment is that the fan motor can actually speed up or slow down to better match the load that's on the equipment. And as you can see in our bullet points, there are some limits that are set. So it says if you have variable speed equipment, the low setting must not exceed 60% of the full fan speed. So there has to be a difference between the fan speed of your low setting and your high setting. And that magical number in this case is 66%. It also says that your fan can't use more than 40% of the power at low speed than it would draw at full speed. And so again, a limitation around the speed of the fan and the power draw of the fan motor. And again, this is essentially just a way of making sure that if you're saying we have variable speed equipment, that it really does function with a lower fan draw and a lower fan speed. And the benefits to this are, being able to better match the load on spaces, better dehumidification when you move air across a coil more slowly, and lower energy use when you have an adjustable fan speed. So like we sometimes talk about, and I think we will in this presentation at some point, matching the ventilation load within a room. We're also looking to match the fan speed to the load that's on the equipment. And in doing so, by being able to operate at essentially different phases, we're able to get greater efficiency out of the equipment. So variable speed equipment is a great thing in our energy efficiency, high performance mechanical system world. When you have it, it needs to meet these parameters so that you actually get the benefits of multiple speeds from the equipment.
So there's our numbers for the chilled water cooling units, and then something that I think we'd probably see more here is DX cooling. So the numbers are a little bit different, but the principles are the same. You want to make sure that your minimum speed is actually saving energy and drawing less power there. So we can move on to the cooling equipment efficiency. So this again is pretty straightforward. Basically, to comply with a simplified approach, your equipment needs to be able to meet certain efficiency requirements. They are in the tables here in the ASHRAE code manual. But one thing to point out, since we are talking about the new codes, is that efficiencies have gone up across the board for ASHRAE 2013. So if you're used to working with an older code, you might be used to speccing out the same HVAC equipment that you have for many years at this point. Just know that you need to look at some more efficient equipment, in general, and especially if you're going to be meeting the simplified compliance approach. Another qualification is for economizers. So Burke, if you want to walk us through the economizer requirement, please.
Sure. So economizers are an interesting piece of technology. Historically, they have sort of come and gone from being required within our Georgia climate zones. And, the reason for that is when you think about how an economizer works. An economizer is basically a function or piece of equipment but on your HVAC system that allows you to bring in outside air at high volumes and flush it through your building essentially when your outside conditions are right. And so, as you can imagine, an economizer might be a really great piece of equipment to have, I don't know, in Asheville, North Carolina, where there's a lot of the time of the year that they have really nice weather. It's 70 degrees outside, the humidity is relatively low, and you can take advantage of the nice weather conditions outside by turning off your condensing unit and using your fan to bring outside air into your building and distribute it through your building, and benefit from the fact that you don't have to dehumidify or cool that air because it is at essentially the conditions you are looking for. And that's what an economizer does. As you can imagine, an economizer probably doesn't get used nearly as much in, let's say, Valdosta, Georgia, for example, right? So even within Georgia itself, you might have extreme North Georgia, places where they could probably use an economizer a couple hundred hours a year, and you go down to South Georgia and you might see some place where they're going to be able to use an economizer, 20 hours a year, because they just don't have that many hours of their, day when the building is occupied and the equipment is on, that the outside air conditions really make economizers beneficial. And the cost of an economizer, putting in the equipment and the controls, might be something that a design team would want to look at not doing. Yeah. Because of all these reasons, if you look back, go back one more, sorry. Because of all these reasons, if you look back at the ASHRAE standard over the years, economizers have essentially come and gone from being required in Georgia. In this cycle of the code, it looks like they are now going to be required in Georgia for larger systems. So that's basically just a functionality of your equipment and its controls. If you put this into a building, you're going to be required to have an economizer. There may be some ways and there may be some motivations for someone to essentially want to trade out of that economizer requirement, particularly if they think they're just not going to be able to get a lot of use and therefore a lot of efficiency or savings out of the equipment function.
Yeah, that's a very good point, because this is a new requirement for this year. Some of our builders might not be used to using those economizers. So there is a bit of a carve out here, even within the simplified approach, that allows someone to basically install more efficient equipment. So I think that might be a path that a lot of our design folks in Georgia take. But keep in mind, what I just talked about was that, efficiencies are kind of going up across the board. And then you compound those higher efficiencies with even more efficient equipment because you're trying to be exempt from the economizer. So you might end up with a much more efficient unit, which is great in the long term, but obviously is going to be going to be very cost prohibitive. So something to consider. But typically, you have to kind of balance the cost of an economizer versus that more efficient equipment. So
I also see listed here some exceptions for places that might not want high outside air volumes or might have limitations around humidity control. So that's another thing to be considered here. I see computer rooms, healthcare facilities, supermarkets. I mean, these are places that have their unique reasons for why they wouldn't want a large volume of outside air to be dumped into the building. So they would, it appears, have an exception, and then anybody else would be able to put in more efficient equipment. And Hugh, I don't know if this is something you would have some commentary on, but I think from the design side, this is a design engineering decision. What works better for us to comply? Do we want to spend money on economizer function and controls because by shutting the equipment off and using the economizer function, we increase efficiency? Or do we want to just increase efficiency in the performance of the equipment because there's less complicated controls required for that, less sequencing, less stuff to go wrong in some ways, and you simply put in a more efficient piece of equipment to gain that efficiency you're looking for?
Well, that depends, because in some cases, yes, the high efficiency equipment would probably be less cost. But in terms of what you're looking for in terms of energy requirement and how low you want your energy bills to be, then the economizer might be the way to go. There are ways to do the economizer with like a small desiccant wheel that will strip the humidity out of the system for the most part, and you can dump 100% air in the building at say 55, 60 degrees thereabout, and that will substantially cut your energy bill over that period. But if it's a smaller business that we're dealing with, a 25,000 square foot or smaller, and you're using a regular split system, then it might be more cost effective to go with a regular high 19 or 21 SEER split system at that point.
Yeah.
And I think a little bit of that is going to be dependent on your climate zone as well, because that climate zone 4, that's a pretty big boost there, 40% to 42% more efficient. So.
And one thing I'd like to add is that economizers only pretty much work with rooftop units, whereas a regular split system may or may not be a rooftop configuration.
Yeah, I actually ran into that quite a bit, working on some projects in Chicago with some fire stations that all happen to have split systems for the most part, because they have multiple zones for bunkhouses and office area, and then the apparatus bay. So there were a lot of split systems. So unfortunately, we weren't able to use a lot of economizers, even though that was in the Chicago area, which is a very good climate zone to use economizers, because you end up with a lot of those shoulder months where the weather is nice outside.
So Hugh, when I hear you say this and sort of looking at these requirements and thinking through it, looking at these climate zones and the percent efficiency if you want to get out of the economizer mode, I look at it and I probably think a simpler system, a building that has a couple split systems that's in climate zone 2 or climate zone 3 probably would look and go, yeah, maybe I'm just going to do more efficient equipment. I can get a 19 SEER heat pump pretty readily, and maybe that lets me hit this spec. On the other hand, if I've got a larger or more complicated building, or I've moved up into a climate zone where I can get more runtime out of an economizer, then it may make more sense to look at the economizer compliance pathway and not try and use one of these efficiency exceptions.
Well, because I guess the way to put it is, if you're using a rooftop unit, right, more often than not, a rooftop unit is going to be a package unit. And package units are inherently, you're doing your cooling, you're doing your heating. It might be strip heat, it might be gas heat, or a combination thereof. Versus if you're using a regular split system, then you're talking about evaporator section, you're talking about a furnace, you're talking about a condensing unit, and sometimes it might be even, bringing in outside air, right? So that might come 10% of your air is coming in through some duct, or you might be using a heat exchanger. So it just depends on how complicated you want the system to become. The cost could start adding up using the split system versus just going with the rooftop and the economizer.
Excellent. All right, next requirement we're looking at here is for heating equipment efficiency. It says heating must be provided by one of these following types of systems, and these are relatively common, straightforward package units or split systems with heat pumps, like we've just been referring to. You could have a furnace system, or you could have an electric resistance heater, and then, of course, we have listed the baseboard connected to a boiler, which seems like a very specific and somewhat antiquated type of system to me, but it is on the list.
I almost left it out, but for the sake of completion, I left it in. And then I think the main point here too is that the heating it must meet the certain efficiency, and again, those heating efficiencies have gone up with the change in the code. So again, check that manual to make sure that the systems that you're using are going to be compliant, so that you can meet these minimum efficiency standards. All right, the next requirement here is for exhaust heat recovery. So basically the system, if you have an exhaust system, you need to be able to recover some of that energy or some of that heat before you dump all that air out of the building. So there's a couple of requirements here, and basically it must have the system that exceeds the value listed based on those climate zones. So again, that's going to be a table lookup in the code book. And then there are two tables based on the amount of hours that the equipment is going to be running. So basically the threshold is 8,000. So if you're less than 8,000, you have to look up one table, and then if you're more than 8,000, it's another. And they must be able to recover at least 50% of the energy. And of course, as with most of the things in the code, there are these different exceptions. So we see this one come up a lot when it comes to either labs or healthcare facilities that they end up having, they end up being exempt from some of these requirements. And also anything that is exhausting toxic fumes or commercial equipment. You're probably not going to be able to extract much of that cooling energy out of the kitchen range hood because it's going to be pretty warm. So, and keep in mind that there are distinctions made between just heat recovery and then that cooling energy recovery. And that's based on climate zone. And we do have how many counties in Georgia? 6 or 7 counties that are in that climate zone 4 that they consider a cold climate. So that would be a slightly different lookup for climate zone 4.
As you can imagine, in commercial buildings, we have outside air requirements. So we're bringing air into the building, and as you learned from our building science module, that means an equal volume of air is going out of the building someplace else. And so as you can imagine, when we've got all this air being pushed into commercial buildings, all this other air has to be pushed out of the commercial building. And that means there are opportunities to do energy recovery from the outgoing airstream. And that's basically what this requirement is saying. You should be doing that. There are exceptions because, as you can see here, a commercial cooking environment or a laboratory environment might not be a good option for energy recovery from your outside airstream. And this typically is because they have either airstreams that may be contaminated in some way or because they've simply got, we'd say, a volume of air that is being moved out of the building that is essentially a process. It is not the outside air that's brought into a standard commercial building is being brought in for human comfort, and we're exhausting air out of the building at the same time so we can do some energy recovery. This process air, there may not be a good opportunity to energy recovery, or it may not be appropriate to do energy recovery, and you look at this air as not really being brought into the building for human comfort like outside air in an office environment, but it is almost being brought in association with a function or a process that's happening inside the building. And so like a lot of other things within the code, when you look in the lighting section, process lights are exempted from your energy code compliance calculation. So in the same way, you would sort of look at this and say there are instances where certain exhaust airstreams from the building are not appropriate for energy recovery.
And there's a reason for that. From an equipment standpoint, most of these buildings that are specialized, talking about like CDC, hospitals, stuff like that, there are special requirement for a certain amount of air for a process or for some function, right, that has to come in. So that air has to move at that rate and nothing else. So that takes precedent over recovering energy. Basically, that's what it is.
Thanks, you. All right, the next one on the list here is thermostatic controls. You're going to see there's a number of things on this list here that are basically tied to what type of thermostat or what type of function that your thermostats have. This one is pretty basic, and it either needs to be dual set point or manual changeover. And that means that essentially a person has to come and switch between the heating and cooling mode, or that there is a degree of deadband, if you want to call it, between the temperature you're heating up to and the temperature you are cooling down to. So, most standard programmable thermostats would do this, or a manual changeover that you physically have to switch between cooling mode and heating mode.
Heat pumps. All right, this one is interesting. This one basically is saying that if you have a heat pump system, right, then the system has to work as much as it can, as low as it can. The heat pump, they're not allowing you to turn on strip heat or gas heat if the heat pump mode can suffice. Basically, because it's going to be more efficient using your heat pump mode rather than going over to your strip heat and or your gas auxiliary heat.
Yeah, this is something, again, my experience in Chicago. I mean, if heat pumps can work in an environment like that, then they can definitely work down here in Georgia. And I think that Southerners are just a little bit afraid of the cold. And I can say that because I am originally from Mississippi, so please don't send your angry letters to our Energy Codes hotline or anything. The point is really just to rely on the heat pump, know that it's designed to reach a certain set point, and then it can do that. I think we're just too quick to jump on that emergency heat sometimes. So taking that control out of the occupant or out of the building owner's hands and just locking that into, say, an outdoor thermostat that's set at 48 degrees, I think that's just going to be a little bit better.
Some people may not be aware there are thermostats that, depending on how they are connected, wired up, you go and you crank the air down more than 5 degrees and you automatically kick on the electric resistant strip heat. So that's what we're trying to stay away from here. Basically, if it's 50 degrees outside and I crank the air down by 6 degrees inside, my heat pump should be able to do the recovery and warm the building up efficiently. I shouldn't need the electric resistant strip heat to come on until I've dipped below the balance point of the equipment. And so this is essentially a requirement that says we're only running strip heat when the outside temperature deems that it's cold enough that the equipment needs the electric strip heat for that heating recovery, which for modern equipment is, especially in Georgia, very, very limited amount of the time. Unfortunately, this equipment can be installed or wired incorrectly and basically have the strip heat running all the time. And it's just extremely expensive. I want you to imagine that instead of your heat pump operating like a heat pump, you now have a toaster oven installed inside your fan blower box, and you're just trying to blow air over the toaster to make it as hot as possible, as fast as possible. Will it give you warm air? Yes. Will it do so efficiently and cost effectively? No. And so this is just a control function to try and make sure that our heat pumps work like heat pumps most of the time.
And also, just to add to that, from a equipment standpoint, heat pumps are typically designed to work down to about 20 degrees Fahrenheit before it starts struggling capacity-wise, right? So you'll get probably most of your capacity all the way down to 20, 25 degrees outside Fahrenheit. Anything below that, 10 degrees, then it starts struggling to keep up with the load.
And Hugh, is it true that typically the more efficient the heat pump gets, the lower that magic temperature number becomes?
Not necessarily. Once you get down to, because you see, what your heat pump is doing is just switching your refrigeration outside and it's bringing your condenser inside. Basically, that's what it's doing, right? So your condenser temperature is somewhere in the 140 degrees thereabout. Right? As long as you can reject heat outside, the closer you get, that delta outside gets smaller and smaller when outside is cold, because you're going against, say, a 45 degrees evaporated temperature, right? So the closer you get to that number, then your capacity starts falling off. Once you clip below that number, right, then your capacity just goes to hell, and that's when the strip heat, strip heat is needed, right?
Yes.
But you don't want to turn it on before that point.
Okay.
So that's where your balance point setting comes in.
All right, another one here, reheat controls. Basically, reheat is a system in which the way I like to look at it, super cool the air within the building to dehumidify it, and then we heat it back up for comfortable air temperature. And in doing so, we may be able to service different zones at different temperature set points with a centralized system. I like the slide that says, in general, reheat is banned with a few exceptions. And so it's like, if you really want reheat or you really need it, like if you're in a typical, like an archives environment where you need a very, very specific band of temperature and humidity all the time, then maybe there are some reasons why you would be using something like reheat. But a typical office building probably doesn't need reheat today. Unfortunately, I was in an office last week where they were saying, oh yeah, it's always cold in here in the winters, and then we have these boxes in the ceiling that have little electric heaters in it that warms the individual rooms back up and warms the air back up. And I was like, I think you're referring to a reheat system. And this used to be something that people would just put into an office building environment, and as you can imagine, it is kind of a cheap way to give you individual control of the reheat within certain areas, so everybody's getting cold air dumped into their room, but Joey wants to go over and he wants his room a little bit warmer, and Hugh wants his office a little bit cooler. So it's a cheap and easy way to give them an ability to adjust that. But as you can imagine, it's not a very cost-effective way to get comfort in those separate offices. So reheat in general is kind of banned out of the code unless you have very tight parameters for your humidity and temperature controls. Like, you absolutely need to hit that particular spec. It is not a good choice for something like a general office building.
Yeah, and that's a good point too. When we're talking about exceptions here with reheat, it is so banned that we aren't making exceptions for the archives or the libraries. In fact, the code just says if you need reheat, sorry, you can't use the simplified approach. You have to go down the prescriptive path. So no exception is really made on reheat except for that site solar energy and a couple others. But typically it is basically outright banned. So that's an interesting thing given how many exceptions there are in the code. So I thought that was kind of interesting. So the next one here is just again another kind of seemingly basic control that's built into thermostats, but again, we have to make sure that it is built into whatever thermostat or control system that you're using. So basically, you have these time lock considerations. First one here, it has to have a 7-day programming window. Older thermostats might have only had, basically weekend versus weekday. But to qualify, you really need that 7-day 7-day control system. You also have battery backup, basically for the timing, so that if you do lose power, you'd be able to kind of retain those settings, because we know that our occupants, our building managers and things tend not to reset those controls either after a loss of power or even after a time change sometimes. And then you also need accessible manual override that allows for temporary operation of the system for up to 2 hours. Again, just temporary. You don't want them just to lock it out and put it in manual mode, and again, just kind of leave it that way. And then you need a setback down to 55. This is a wintertime condition, and then 90 in summertime condition. These kind of setback periods based on occupancy. You don't really need to run the heat or the cooling while the building is unoccupied. So any other things to add here when we're talking about time lock controls and thermostats?
Well, I thought what you just said was interesting. It reminds me of a lot of conversations we have around the code, and you see it here on the slide, is capable of temperature setback, is capable of temperature setback, is capable of retaining programming. Yes, this requirement says you need a 7-day-a-week programmable thermostat with battery backup, which is a real common piece of equipment that you can go buy at any big box, home improvement retailer off the shelf right now for 20, 30, 40 bucks. Certainly there are more complicated controls that will do the same thing. So it's a pretty standard piece of equipment, and people often make or I say get confused between the functionality requirement and the actual operation of the building. So there's nothing up there that says you have to set your thermostat back to 55 or you have to set it up to 90 or even 78 in the summer, in cooling mode. How you use the equipment is really up to the person who operates the building, but the equipment must have this basic functionality. And essentially what you're doing there is saying, yeah, people need modern thermostats installed. We don't want to build a new building and put in literally a slide scale thermostat that you either click on or off and you slide scale to the temperature you want.
I'm a big fan of that.
We want modern equipment in modern buildings, and even this equipment with all of these functions and features that you've just listed, it's something you can go get off the shelf at your big box home improvement store for 40 bucks.
Sure. Yeah, and that's a good point too. It is capable of is the operative phrase here. Buildings this small, going down the simplified approach, don't really need commissioning, but it's never a bad idea to actually go in and have someone set up the thermostat so that it actually is taking advantage of some of these settings. But maybe that's a different webinar that we'll work on at some other point we need more commissioning. And the next one here, a pretty standard requirement for refrigerant pipe insulation. We need to have it. It needs to be at a specific R value, and most important, and I think most often forgotten, is it needs to be protected from the elements. So we've all been on roofs and seen that foam insulation even after a few months, or that it just deteriorates to nothing once it gets to the elements. So that's something that we really need to see more of, and it's a requirement in this part of the code. So any good stories of deteriorated insulation or anything like that?
Oh, the pictures I could show you of deteriorated pipe insulation. I mean, I think the thing that I would highlight on this is essentially this is a requirement, and it's one of those things that I think gets overlooked a lot. Yeah. We see hot water systems that don't have adequate insulation on them all the time. And I think people think, oh, it's a little thing. And it is, but this is a code that's constructed around a package of things that you should do to create an efficient building. Right. And so each of the things in that package is important. And in this version of the simplified compliance pathway, this is on the list, so it's required. And I think that it's one of those things that, pipe insulation and pipe insulation protection just probably gets often overlooked in the real world. So I think that's one of the values of running through a simple list like this. And instead of saying there's 250 things you need to figure out about this building, we're able to say, there's 18, and one of them is pipe insulation. And just do it right.
Yeah, I feel like we've made it pretty easy, right? There are 18 requirements, so this is obviously important. So stick to it, or else the next version of ASHRAE is going to have 24 requirements or 30 requirements, right. And then it's not going to be a simplified approach anymore. So next up, we have DUCTWORK. Again, fairly straightforward here. DUCTWORK and plenums must be sealed and insulated. There are tables which tell you how much insulation you need based on if it's a cooling-only duct, if it's a duct in a plenum location, or depending on which climate zone you're in as well. So again, make sure that you're insulating those up to the requirement. Insulation, duct insulation is really important. We talk a lot about this in residential, but really it's about condensation. You never want to have the warm, moist air touching that cold surface on the ductwork and making that condensation. So really important. We see this a lot. We get a lot of complaints of why are my ducts spitting out water and things like that. So you really have to see that insulation there, and they need to be sealed as well. So generally, what are we sealing that with, Burke?
I mean, typically they're sealed with tape or mastic. Yeah. And as you mentioned, I think we have almost a bigger focus on this in the residential world, where we have hammered into people the importance of duct sealing, and we have trained people on how to do duct sealing, and we have requirements in our code for testing, for not only sealing the ducts, but testing the ducts for tightness. And over here in the commercial world, on one hand, I think we benefit. A lot of duct systems in commercial buildings are inside the building envelope. And in that way, the duct leakage is not as much of an energy penalty. Duct leakage is a big energy penalty when the ducts are located outside the building's thermal envelope. In a house, in a residence, that's very typical, where duct systems are just up in an attic and the insulation is on the ceiling. And so they're up there and they're outside of your thermal envelope. They're outside of your building. And therefore, when they leak, everything they leak is a waste of energy. It's all energy waste outside of your building's envelope. In a commercial building, sometimes we see that. There are still small commercial buildings built with insulated ceilings and vented attics just like houses. But a lot of commercial buildings do have their duct systems and their air handlers inside the building envelope. And because of that, they benefit. The duct leakage is not as much of an energy penalty. But as you said, we also have concerns around condensation. We also have concerns around just performance and comfort. I always remind people that whether your ducts are inside or outside of your building's thermal envelope, if 30% of your airflow is going somewhere other than where it's intended to go, you're not going to efficiently achieve comfort.
Well, and that's part of it too, because on one hand, the condensate issue you'll find more in where the duct is inside the building and inside the cooling space, so to speak, right? And on the energy lost issue, you'll find it more like in the attic. If it's leaking, you're losing 20-30% of your conditioned air is just going to wherever, right? And either way, it's not going to benefit the building. So yes, insulation extremely important with HVAC ducting system.
And I think our footnote here is it sounds really easy to say you have to seal your plenums and your ductwork. There's a lot of connections and joints and seams and takeoffs that actually go into doing that correctly. And it probably doesn't get as much focus as it might deserve.
Sure. Burke, you talked a little bit about air balancing there, so why don't you take us through the duct balancing requirement here?
So duct systems must be tested and balanced, and it's an interesting sort of code way of speccing this. It says balanced to industry standards. We typically say that's within 10% of design flow. This is a big one, and this is another one that I think is probably often being ignored in that someone puts balancing, maybe they say we're gonna do system balancing, but like, does it actually happen? Does a report actually get generated and submitted? And then if it does, was the testing actually done, or did somebody just sort of go, oh yeah, you know?
Most
I'm
of
sure
what
it
I've
was fine.
seen on these light commercial buildings over time is that the contractor would be balancing the system, or so he claimed, but he's just using like a thermometer, right? So he's looking for a certain temperature at certain thermometer, and that's what he's using to balance the system, you know, because these equipment are pretty expensive, and not a whole lot of people have access to them, right?
Yeah.
And so God knows what you're going to find out there when a system is said to be balanced if there's not a report to go with it.
Yeah, speaking of the report, here's what one would look like. Again, if you're lucky enough to get one, but you know, if we're going down this pathway, we have to be able to see this in order to meet the code. So you know, there are going to be temperatures in there at some point, your delta T's, but for the most part, we're looking at airflow measured in CFM, usually using something like that flow capture hood or something like that.
And when we say, you know, that first slide again said to industry standards, Hugh, would you generally agree with that? People are looking at a 10% type of range. What would you consider an industry standard to say, yes, the system is successfully balanced correctly?
10% can be large, right? Because if you're doing 10% per grill, that could add up quite quickly. So I would say the closer you get to your design number is the better you're going to be.
Okay. Pause.
This is cool. It's magnetic. It's awesome. We, unfortunately, there are no other flippin' rooms available at this hour.
I have that. So let's, you know, because you want content, you want multiple voices talking. So, yeah, but let's try and wrap it up.
All right.
All right, automatic dampers here. So the requirement here for 14 is saying that your damper has to be either a gravity type damper or a motorized damper. More often than not, what I'm seeing in the industry is really the neither motorized nor gravity, right? It's usually the ones with the hand, the cheaper ones that you use your hand and balance. So now this is a new requirement that's going to probably add cost to your project, but it is the law of the land, and that's where we have to go right now. I personally prefer the motorized damper. It's a more accurate system than the gravity-fed damper, because the gravity-fed damper is basically, if there's no airflow, it's closed, and when there's airflow, it opens, right? So it's basically a backdraft damper, not a balancing damper, so to speak.
Okay.
I have seen exhaust dampers not included on exhaust systems, like just outside air systems. We see them missing all the time. People put them on the design and they literally don't get installed in the field. So definitely something to check for. All right, another thermostat related requirement. Thermostats that serve the same zone must be interlocking. And as you can imagine, this is because you don't want to have one thermostat in heating mode and another thermostat in cooling mode, and they're just duking it out with each other to see, you know, who wins the space. Does that sound efficient? No, of course not. It sounds terribly inefficient. Plus also you're going to roast some people and freeze some people, right? So a little, all joking aside, this requirement is very straightforward. You can understand why you don't want to set thermostats servicing the same zone, one to heating mode and one to cooling mode. And this just says you should have the equipment interlocked in a way that that's not functionally possible. Another requirement, optimum start controls. Systems that have more than 10,000 cubic feet per minute of supply air capacity are required to have these smart controls. And this is basically just a type of control function in the thermostat that allows it to learn how you use the building and to adjust when it brings the equipment online so that that aligns with when you're going to need the space conditioned. One way we typically look at this is like the difference between warming the building back up in January on Monday morning versus the difference between warming the building up in January on Tuesday morning. Monday morning, the building's been colder and less unoccupied for a longer period of time, so maybe the system learns that it needs to come on at 7 a.m. In order to get to your desired thermostat settings by 9 a.m. versus Tuesday afternoon, you don't have as much downtime, or Tuesday morning, and you're able to bring the system on at 8 a.m. to hit your desired set points when necessary. So those are sort of how these optimum start smart controls function in a building.
Yeah, and here we just have a cooling season example here. So again, it would depend on the time of day and really kind of staggering the load of the HVAC, the heating or the cooling, based on the time and how cold it is outside, because you don't want to, if it can just run all the time and you're still not going to be able to hit that set point at certain times of day, and especially if you have many systems and they're all calling for heat or calling for cooling at the same time, you could be in trouble. Next one up is demand control ventilation, which is a requirement if the building or this area falls under these parameters. So you want to make sure that you have some sort of demand control ventilation. Here we have an example of something that you might see, might be a CO2 sensor connected, so that when the building space goes over a certain CO2 limit, that it's going to allow more outside air to come in through an economizer or through a DOAs or whatever your system is. So, and here we have kind of a graph that shows various techniques of bringing in ventilation. I think you can see kind of in that background, that yellow color, that's just fixed ventilation turning on at about 7 o'clock, turning off at about 7 o'clock, running at full blast that whole time. That's probably not going to be very efficient. So you have various other methods that are more and more efficient, but if you look at the foreground, you see that green color, that's going to be your CO2 sensor, which looks to be pretty much the most efficient because it's going to run that ventilation only when you need it.
And that's really the key of demand-controlled ventilation. The chart does a great job of showing you're required to do this outside air, this ventilation in commercial buildings. If you don't have any control, you basically, have to ventilate at full rate all the time. So you see that big yellow block. There is a lot of energy savings and cost savings that's associated with matching your ventilation load to your people load. And ventilation is essentially for people. And so what we're able to do here is you see our orange bar of people showing how the load of people is moving through this space throughout the day. And by having these demand-controlled ventilation functions, we're able to match the ventilation in the room to the load of people. And in doing so, save a lot of energy and save a lot of dollars.
Wow, are we at 18 already? So the last requirement here is for door switches. So if you have a building, you don't want, if you have a building and outside doors, are, I'm getting so excited that we're here toward the end. The outside doors are open for a long period of time. They're letting in a lot of that outdoor air that you basically turn off the heating and cooling at that time. So here is a system. I'm sure there are many different types of systems out there. But essentially, we don't want to be cool in the neighborhood, as my dad would say. So that's basically what this is about. And so keep that in mind. This is a requirement for the simplified approach. And then, of course, there are exceptions. You know, if you are a warehouse or something and you have rolled-up doors, obviously those are going to be exempt because those are going to be open most of the day. So, of course, like most of the parts of the code, there are some exceptions. Anything to add on our very last one?
I don't think so. I think this is a great summary of the simplified HVAC compliance pathway within ASHRAE 90.1 2013.
Okay. Well, thank you very much for joining us. Again, if you have any technical assistance or training requests, please direct those directly to Southface. You can catch us there at the email address energycodes@southface.org or at the phone number listed. Thank you very much again for joining us on this webinar.
Woohoo!